I'm going to use the board instead of PowerPoint. Everything I cover is on Blackboard. There's a set of PowerPoint slides. But instead of flipping through those slides, I'm going to try and use the board and see if that makes this any easier or to understand or better for you or me. I feel like when I go through the slides, I'm not sure that, I don't know if I'm going too fast, if I go faster through the slides. I think I do. I think I go faster if I'm using PowerPoint slides. So let's try it this way. We'll see how it goes. But the slides are on Blackboard, so you can use that for review. Last week, we started talking about using integrals, and I went through this asphalt problem. And we talked about integrals as the opposite or of derivatives or the antiderivative. Yasmin? Yes. And the benefits of using integrals as opposed to trying to take the area under the curve and divide it into rectangles. Integration is faster and it's more accurate. You cannot get the true answer unless you use integration. So somebody had asked last time about, how do you do these things? And I explained like using, I think, the sine curve, for example. If you want to know what the derivative of the sine is, the derivative is the slope of the curve at any given point. So if you look at the sine curve and you figure out what the slope is at various points and plot that slope, what you get is the cosine curve. So you can derive those derivatives. Or you can look in the back of your textbook. There is a table of derivative rules, and there's a table of integration rules that make this simpler. For this class, those tables are what you need. When you get into calculus, they may tell you, show through algebra or show through the use of the slope how the sine and the cosine are related in terms of derivatives. But for this class, you can use those shortcuts. And so those derivative rules and integral rules are in the back of the book. And at the end of the class, last time, after going through this integration of a curve that you recall, it was a driveway and they were going to add some paving, and the area they were going to pave was here, and this curve had an equation such that it was in fact a quarter circle with a 50-foot radius, right? So if you had stopped to think about it for just a minute or two, you may have realized that this area is simply the area of the square minus the area of the quarter circle. So you wouldn't need calculus. And the point of talking about this is that calculus is a tool. You use it when you need it. If you're going to hang a picture on the wall, you can use your thumb and a thumbtack. You don't need to use a sledgehammer. Right? It's just a tool. This is a simple example, and I gave you, or I showed you in Excel, a different example where the curve looked something like this. This is very much exaggerated compared to what's in the Excel file. And I said, find this area. Well, that is not a simple quarter circle minus, or area of a square minus a quarter circle. To find that area accurately, you've got to use integration. You can take rectangles and find the area of each rectangle and sum them all up, and you're going to find that it's close, but it's not the true area. It's going to overestimate or underestimate depending on how you draw those rectangles. So I want to go through another example and then talk about how it's applied in statics, and if we have time, talk about how we apply this integration in dynamics. If I don't have time this time today, it'll get covered next week. So engineers deal with work a lot. Anybody know what the definition of work is in engineering terms? No, it's not energy or power. It's force times distance. Force times distance. So if you have a ground surface and you've got a block, you can apply a force, and let me do it this way. So if you apply a force on this block over some distance, x equals 0 to x equals d, there's a certain amount of work involved. And we can determine this. If work is constant, we can plot this. So if we think of this as x and F, so there's a force applied over some distance. And if the force is constant, doesn't change as you push this block, the work is simply the force times the distance, right? It's the area of a rectangle. It's also the area under this curve. If the force varies, then we need to use integration. And if this is F and X, we can say that W is the work. The work is equal to the sum of F, X, I, right? And we go back to that rectangle analysis where you draw a rectangle. So the force over each xi, and you sum them all up, gives you an estimate of the work. As xi gets smaller and smaller and smaller, the number of rectangles gets bigger and bigger and bigger. It approaches infinity, and this becomes the integral of f of x, the force as a function of x dx. So if we have an equation that describes that line, we can integrate that equation. That gives us the area under the curve. And if we integrate that equation, the area under the curve gives us the work. Right? Is there a question? All right. So let's say that f of x is equal to 2x squared plus 3x plus 4. And we want to find the work it takes if we apply that force to this block over a distance of 1 meter. So D is 1.0 meters, and this force has units of newtons. We could define xi as, say, 1/10 of a meter, right? Solve this equation for f of x at 0, 0.1, 0.2, 0.3, all the way up to 1.0 meters. Sum those all up, and that would give us an estimate of the force, or of the work. If we integrate this, we'll get the answer much quicker, and it'll be the exact answer. So we're going to take the integral of f of x dx, and that integral is going to go from x equals 0 to x equals 1.0. Right? So when you've got a function such as this, you can integrate each part of it separately. So this is equal to the integral of 2x squared plus the integral of 3x plus the integral of 4. And there should be a dx for each of these. And each of these are going to go from x equals 0 to x equals 1. So do you recall the rules of integration? The integral of a function is the function whose derivative is the integral, right? We're looking at the opposites. So you want to find a function whose derivative is 2x squared. The function whose derivative is 2x squared, well, remember derivatives, we multiply by the exponent and then divide by the exponent. Integrals, we do the opposite. For derivatives, we multiply by the exponent and then reduce the exponent. For integrals, we do the opposite. We'll increase the exponent and then divide by the exponent. So the integral of 2x squared is 2 times x cubed, increase the exponent, divide by 3. And that's going to be evaluated from 0 to 1. Plus the integral of 3x, is 3x squared over 2 from 0 to 1. And the integral of 4 is going to be 4x, because x, this is essentially 4 times x to the 0 power. So we increase it and then divide by it. Yes?
What is that line? Like, I don't get that line.
That line simply says that we're going to evaluate this function from 0 to 1.
So, did you just add 1 to the exponent and then divide it by that number of exponents?
For this, yes. So if you want to take the integral of x to any exponent, call it n. The integral of x to the n is equal to x to the n plus 1 divided by n plus 1. And this is going to be from 0 to 1 as well. Okay, does that make sense? All right. So if we're going to evaluate this from 0 to 1, what that means is we evaluate it at 1 and then subtract the function evaluated at 0. So let me come back over here. So we're going to take 2 times 1 cubed over 3 minus 2 times 0 cubed over 3. And then we're going to add to that the next component of the function, or the next part of the function, 3 times 1 squared over 2 minus 3 times 0 squared over 2, plus 4 times 1 minus 4 times 0. Does that make sense?
You only take the I and the low, whatever, even if that was 10 and 0.
So you would evaluate it from 0 to 10, then you would put 10 in for x and subtract from it the function with 0 in for x. Yeah.
So, if you have, for example,
You mean if I was going to go from 0 to 3?
Yeah.
So then I would have 2 times 3 cubed over 3 minus 2 times 0 cubed over 3. Yeah. Does that make sense? All right. So what you'll often see, though, when you do integration like this, where you're doing it in parts, since each part is evaluated from 0 to 1, you'd more often than seeing the evaluation in this form, what you would see is 2 times 1 cubed over 3 plus 3 times 1 squared over 2 plus 4 times 1. Take the entire function evaluated at the upper limit, and then minus the entire function evaluated at the lower limit. And it'll come out to be the same thing. But this is a more common way of expressing that. So this whole thing goes to 0, and we end up with 2 cubed 8/3 plus, no, that's not 2 cubed, it's 2/3. 1 raised to the power of 3 is 1, so it's 2/3 plus 3/2 plus 4. Say that again?
It's a minus, right? Unit? Because it's a minus right there.
Oh, well, I was evaluating this, so we could do it this way. Up here would be 2/3 minus 0 plus 3/2 minus 0 plus 4 minus 0, which will give us the 2/3 plus 3/2 plus 4.
I have a question. Why would that be the same? The signs are different. So
Well,
instead of the second one, the first one and second one are the same.
yeah.
Why would that be the same?
Well, because this is, if you just go back to the rules of arithmetic, if you're adding two parentheticals, you can drop these parentheticals. This is 2 times 1 cubed over 3 minus 2 times 0 cubed over 3 plus 3 times 1 squared over 2 plus a negative 3 times 0 squared over 2. So you can just, what's that? What was that word? Distribute, thank you. You can just distribute this, and you'll come up with the same answer. If you want to, if you go through this, 2/3 minus 0 is 2/3, right? And that's what we have here. 3/2 minus 0 is 3/2. 4 minus 0 is 4. So again, we can use the rules of integration in order to come up with this value much quicker and much more accurately than if we just use something like an estimation using rectangles. All right. Question?
Yeah, I'm lost kind of back here.
Okay.
2x to dx. Why? I don't understand why.
So we're going to take the integral of 2x squared with respect to x. That's what the dx means, with respect to x.
But the derivative would have been 2x.
Well, if you look at this function, what's the derivative of this function? Multiply by the exponent and then reduce the exponent, right? So multiply by 3, and it cancels that 3. And then you reduce the exponent from 3 to 2, and you end up with 2x squared. So I want to get these words exactly right because it gets confusing. And I wrote them in the previous slide. Or in the previous slides from, I guess, last week. So the integral, when you want to find the integral, you want to find the function whose derivative is this.
I've been thinking in terms of differentiation rules, not variable rules.
Ah, okay. All right. So this is, one place where we're going to use, and where you're going to use integrals throughout the rest of your academic career and into your engineering career. It makes life way easier and much quicker. This was a fairly simple and straightforward function, right? And again, if you go to the back of the textbook, it'll tell you that the integral of x to the n is x to the n plus 1 divided by n plus 1. In the back of the textbook, it'll give you the definition for the integral of sine and the integral of cosine and things like that. And so if let's get rid of this. Can I erase this? All right. So if we had, instead of that function, let's say we had f of x is equal to 2 times the sine of pi over 2x plus 3 times the cosine of pi over 2x. And you want to find out the work done by that force over some distance. And we'll say again that the distance is equal to 1.0 meters. The work is equal to the integral from x equals 0 to x equals 1 of f of x dx. This is f of x. So the integral from x equals 0 to x equals 1 of 2 times the sine pi over 2x plus 3 times the cosine pi over 2x dx. Because we've got two components that are added together, we can integrate this in parts, integrate the first part, and then add that to the integral of the second part. So, who's got their textbook? Look in the back of the book and see if you can find the definition for the integral of sine times something x. Sine omega x is. All right, so let me do this over here. I'm not sure what page. It's way in the back. It's in one of the appendices. It's one of the last pages of the textbook. So the integral of sine omega x is equal to what was that? Plus c. Okay. All right, so this is in the back of the book. So you find this, and now if you recall from last week, I talked about this integration constant. Whenever you have an indefinite integral, you've got to include this integration constant because the derivative of the derivative of that function is equal to the sine, omega x, right? The derivative of this function plus 10 is equal to the sine of omega x. The derivative of that function plus 100, plus 1,000,000, plus anything is equal to sine omega x. So when you have an indefinite integral without any limits, you've got to include that constant of integration, which is just the letter c. But if we evaluate this from, say, 0 to 1, that would say then we evaluate this function at 1 and subtract its evaluation at 0. Minus 1 over omega cosine omega times 1 plus c. And then subtract minus 1 over omega cosine omega times 0 plus c. Right? And because we have these limits, the constants drop out. When you evaluate this entire function, you've got a plus c minus a plus c, so the c's cancel out, they go away, and you don't have to worry about that constant if you've got limits on your integrals. So this is the integral of the sine of omega x. What's the integral of the cosine omega x? What is it? Oh, okay, all right. Plus what? No, the integral of cosine.
Oh, the integral of cosine, okay, so we went over omega.
Right. Plus c if it's indefinite. So we can use these rules to evaluate this function. So we've got an integral of a constant times a function, so the constant doesn't change. 2, and the integral of sine, pi over 2 in this case, is omega. So the integral of sine omega x equals minus 1 over omega, minus, in this case, omega is pi over 2, so 2 over pi is equal to 1 over omega, times the cosine of omega x. And then we add to that 3 times the integral of the cosine omega x, which is 1 over omega sine x. And this entire function is evaluated from 0 to 1. Okay? Can you put your phone away? Well, if you've got an emergency, you're free to step out and take your call. All right. So we go through this is algebra at this point, right? We're going to plug a 1 in every place where we see x, evaluate the function, subtract from that this function with a 0 in every place we see x. Sure. Let me erase this. And I will write down what you tell me. All right. Go ahead.
So it's going to be negative 2 cosine pi equals to pi 2 times
Oh, okay. Oh, so you want this over pi over 2? Okay.
the same thing.
Yeah.
Right?
Yep.
Okay. Plus 3 times pi over 2 over pi.
That should be, let's see, a 1, and that's over pi over 2. Okay.
Minus 2 cosine pi over 2 times 0 over pi. Plus 3 times pi over 2 over pi. So the first
Hold on. Yeah, you're getting ahead of me. Okay. So what is that equal to?
So then it's like negative 2, 0 over pi over 2. Because, okay, so pi over 2 times 1 is pi over 2, and cosine pi over 2 is 0.
Right, okay.
The same thing with sine pi over 2 times 1 is pi over 2.
So this first function is 0.
Yes,
Okay. And what happens to this function?
it becomes 3 times minus pi over 2.
Okay, so how about if we do it this way? 3 times 2 over pi.
Yeah,
Okay.
and then
And then we're going to subtract.
the first one is negative 2 times 3.
Okay.
And then the second one is
Oops. Right.
so, like, basically I added 6 pi to, I mean, 6 pi, 6 over pi. Plus 4 over pi. This is the same pi.
Yes, that's it. Good job. And if you plug in the value of pi, it comes out to be 3.1, 3.2, somewhere in there. So again, most of the work we just did here was algebra. I mean, most of the work you're going to do is algebra, but knowing those rules of integration means it's a lot less algebra. And it's a much faster, quicker. And here's the thing, which is even more, what's more important than the fact that this is faster is that it's exact. It's not an estimation. It's not a guess. It's not an approximation. That is exactly the area under this curve. The other methods we talked about were approximations. And if you've got a really super complex equation, it might be faster. It may not even be possible to integrate it. There are equations out there that you just can't integrate. And those you have to solve numerically. That's a whole other world. But in general, integrate these equations and you get the exact answer in a much faster time allotment or time period. Okay? All right. So what I want to do now is give you a couple of examples of how this stuff is used in like real world engineering stuff. So let me go through at least one example of how it's used in statics. We'll see what the time is, and then either go through another example in statics, or I'm debating about whether I even get into dynamics at this point. I might just leave that for next week. So I'm going to erase this. It's okay? All right. Now this is one place where the slides will be much more useful for you because my artwork is kind of bad. But I'll put some stuff on the board and you can look at the slides when you have time. So, integrals in statics. So statics in engineering means analysis of things that aren't changing in time. They're static. They're just sitting there. So you can imagine one of the most common analyses in my field is looking at forces on a dam. Right? So if you have a river or a lake, and that upside down triangle is a symbol we use for an open water surface, and there's a dam, right? And here's the ground surface. There's a lot of pressure on that dam. The reason dams are real wide at the bottom is because all this water is trying to push that dam and make it flip over. So you make it wide at the bottom so it's more stable. So there's all of these forces pushing on this dam, and we can use integrals to evaluate that. In order to get to that point, trying to evaluate a force that might be acting over 5 or 10 or 100 or 200 feet. I mean, think about, I don't know how familiar you are with the dams out west, Lake Powell and Lake Mead. Their dams are 200 feet tall. They've got water that's 150 feet deep. So you could try to evaluate this system with a force that's acting over the entire surface. But there are engineering principles that would tell you that if you take that force and apply it at the center of gravity, a point force applied at the center of gravity is equivalent to a distributed force applied over the entire face. So the key then is find the center of gravity here. And sometimes it's pretty easy, right? If this were, let's say this was a fairly poorly designed dam, right? That's not a very good dam. Where do you think the center of gravity is? Like right in the middle. If you've got maybe a dam that, let's do it this way. Might have a dam that looks like that. That's a little bit more complex because you've got these two legs. And it's entirely possible that you find that the center of gravity acts out there someplace. Sometimes, especially rock arch dams, will look, let's see, how would this work? They sort of lean into the water. So, and they're built into the ground and they're built into the walls. But they're built up as the water fills up, because if you just drain that thing all out, it falls over. But in all of these cases, knowing the center of gravity is important, because that's where all of this hydrostatic, all of this water force acts, essentially on that center of gravity. And you want to make sure that a force acting on that center of gravity is not going to push your dam over or push it out of the way. So you need to know where that center of gravity is. And we can define the center of gravity as equal to XI over A, and then the y component is equal to the sum of the YI AI over the sum of the A's. So let me explain what this is. Imagine you've got, let's say you've got a triangle. You divide it into rectangles. So you've got each rectangle. Each rectangle is XI wide, YI tall, and XI times YI is the area. So for each rectangle, you take XI times its area, sum all of those up, and then divide by the sum of all the areas. And you get the x component of the centroid. You should just put it away. Yes?
How are you going to find the sum of all areas?
Exactly. And the same for y, we'll do the same thing for y, and I'll show you, assuming there's time. You can do this either vertically or use horizontal.
So how do you find the area of one rectangle?
Well, we won't. We don't need to because we're going to do integrals. So instead of taking the sum of xi, ai, as xi gets smaller and smaller and smaller, it approaches where am I at here? Well, let me work through this because it's a couple of notes ahead, but we will end up with the integrals. We don't have to figure out the individual areas. So let's look at something that's not quite so simple as a triangle. Let's say we have some object that's sort of a semicircle. And this line is defined by some function so that y is equal to some function of x. And we're going to try and find, here's the center of gravity. We want to find x bar and y bar. That's what we're going to try and find. So if we start with a single differential area, that rectangle has some differential area. The centroid of this rectangle for that differential area, x bar is equal to x, whatever this value of x is. And y bar, if it's a rectangle, where's the center of gravity? Right in the middle. So y bar is equal to 1/2 of y. And y is given as a function of x. And so it's a function of x. We can call it y as a function of x like that. And then this is y of x over 2. So whatever equation defines this line, if you evaluate it at this value of x, you get y of x. Divide that, which is this point right here. That's the top of your rectangle. The centroid is going to be at the midpoint, so it's going to be y over x divided by 2. Okay. And then dA, well, for a rectangle, dA is simply the width times the height. So it's equal to x bar times y of x over 2, which is y bar. I'm sorry, it's y of x. The area is y of x, not y of x over 2. Okay, does that make sense? Okay.
Wait, why is it not?
So we're looking at the total area of the rectangle. So the area of a rectangle is the width times the height. And the height is given by y of x. So what's the value of y at this value of x? It's y, right? So the area is the width, x, times the height.
So then what is
Y over x over 2 tells you the centroid, the y component of the centroid.
the gravity?
Yes, the center of gravity. Yep. So, you know, I gave you some examples of center of gravity, but, you know, you can look at the pen too, right? Where's the center of gravity of the pen? It's the point where it'll balance. If you're going to balance this thing on a single point, it's got to be on its center of gravity. And you might look at the pen and say, well, it's in the halfway point, but it's not, because the tip is heavier with the ballpoint and all that extra plastic, so you got to find it someplace in there, and it's not going to let me do it now, kind of like that. So the center of gravity is someplace towards the front of the pen, not quite in the middle of it, but that's another way to think of the center of gravity is if you take this object and balance it on a point, you have to balance it on the center of gravity for it to stay balanced. All right. So we have this expression for x bar and for y bar in terms of summations. And we can, as I said, as xi gets smaller and smaller and smaller, this approaches the integral. So we could say that x bar is equal to the integral of x dA, and the integral over the integral of dA, because the sum of the area is the integral of dA. And the integral of x dA is the integral of x. Here's an expression for dA. X y of x dx. So the value of x is x. The value of dA is x y of x. X y of x. And this should be a dx here, because if you're going to take the derivative, you've got to add a derivative on that side. What's the integral of the derivative of any function? Right, so the integral of a derivative of a function is the function. So the integral of the derivative of area is area. Now, if you didn't go that far, you could always say that this is x times y of x dx divided by dA, the integral of dA, which is wait a minute. What did I do here? I dropped something. The area. That's what happened. All right, I apologize. This should not be there at all, actually, because your dx is here. It's the width times the height. The dx is the width. So x times dA is x times y of x dx. So that's x times y of x dx, and dA is the integral of y of x dx. And then we can look at y bar. Over here is the sum of y times a, which would be the integral of y. Y bar is y of x over 2. Times dA, which is here. And then that's divided by the integral of dA, which is y of x dx. Okay? Yeah?
So we're taking the integral in respect to y.
Taking the integral with respect to x. That's why, so the dx tells you what you're taking the integral with respect to. So this is x, y of x dx. So it's the integral with respect to x. All right?
I'm confused why we put y x over 2 brackets.
So for the y parameter, we're looking for the y component of the centroid. And we said over here that the y component of the centroid is equal to the sum of yi, ai. Okay? Yi, ai over ai. And yi is y over 2. The centroid of a differential area is 1/2 of its height. So that's y of x over 2. So y of x over 2 is the yi component. And ai is y of x dx from here. Okay. All right. Okay. So with that, now we've got these two functions that we can integrate, and let's see. Let's say that for this function, let's say, let me come back. Let me come over here. Give me some more board space. Let's say that y of x is equal to minus x squared plus 4. So if y of x equals minus x squared plus 4, when x equals 0, what does y equal? 4. And if y equals 0, what does x equal? 2. Which tells us that if minus x squared plus 4 defines this line. Right, so when x is 0, y is 4. And when y is 0, x is 2. So that gives us the limits that we need to integrate over. All right. So if we start with our equation, let's start with this one. And we integrate that. So we'll come back here. I'm going to get rid of this. We're going to say that x bar is equal to the integral of x times y of x, which is minus x squared plus 4, dx, over the integral of minus x squared plus 4 dx. And we're going to integrate both of those. Let's see, x goes from 0 to 2. So in order to do that top integral, you've got to multiply the x all the way through it. Which would be minus x cubed plus 4x dx over minus x squared plus 4 dx. And now we have a summation. We can do the integral in parts. I'll leave that drawing for as long as I can. Let's see. So the integral of minus x cubed. What's the integral of minus x cubed? Yes. So minus x to the 4th over 4 plus the integral of 4x. What's the integral? Yeah, so it would be 4x squared over 2, which is going to come out to 2x. And that's going to get evaluated from 0 to 2. And we'll divide it by the integral of minus x squared plus 4, which is minus plus 4x from 0 to 2. So this is, I'm going to try and save that wonderful artwork for a few minutes. Minus 2 raised to the power of 4 over 4 plus 4 times 2 squared over 2. And we can divide that by minus 2 cubed over 2 plus 4 times 2. And since 0 is going to go in every place where there's an x, it just comes out to be 0. Okay, and that comes out to be 3/4. Minus 2 to the 4th over 4. Yeah, there's a negative here and here. So, assuming my math is right, I got 3/4. So that means that if x goes from 0 to 2, the centroid of this is at 3/4 on the x direction. The y direction we have to evaluate yet. So the y direction, we can pull the 1/2 out, and then we have y of x squared. Yes? You got it? Okay. Okay. So we have to plug the function in. I mean, you might be tempted to just say this is equal to the integral of y of x, because they can't y of x squared over y of x equals y of x. You can't necessarily do that. So let's just play this out. 1/2 times the integral of minus x squared plus 4 squared dx over the integral of minus x squared plus 4 dx. And if we square this function, we end up with, come down here, 1/2 times the integral. And again, this is with respect to x. So even though we're looking for the y component, we're still integrating with respect to x. So the limits are still 0 to 2. And minus x squared plus 4, that quantity squared is x to the 4th minus 8x squared plus 16 dx over the integral from 0 to 2 of minus x squared plus 4 dx. And so again, integrals in parts. The integral of x to the 4th, x to the 5th divided by 5. The integral of minus 8x squared is minus 8x cubed over 3. The integral of 16 dx is 16x. And we're going to multiply through by 1/2 as well, but I'll just keep that out for right now. Yes? Minus x cubed Yes, it should be. The number that I gave you here, it should be right. I just have I miscopied that. Yes. X to the fifth, 8x cubed over 3, 16x. Yeah. So, if you plug the value of 2 into here, well, let's start this way. If you plug the value of 0 into this function, it comes out to 0. So we can just drop that, plug in the value of 2, and if you do that, this comes out to 8/5, if my math is right. Which means 8/5 is 1 3/5, a little bit more than 1 1/2, right? That's 4, that's 2, that's 1. So the y component is someplace here, and there's your center of gravity. Bless you. 8/5 xy components are 3/4 and 8/5. Okay. So, right, so the 1/2 was part of the function, and because it's a constant, I take it out of the integration. When I integrate the function, I still have to carry the 1/2, and that gets multiplied through. So you can evaluate the parenthetical and then multiply by 1/2. Yeah. Yes?
Is it 0 over 0 and independent one?
It would be because you're dividing by, let's see, 0. But you can resolve that issue, let's see, by you're actually taking the integral of the numerator divided by the denominator. So if you take the integral of the numerator, evaluate it from 0 to 2, and then take the integral of the denominator and evaluate it from 0 to 2, the denominator is not 0. Yeah. Okay. Other questions? All right. Well, so that tells you where the centroid is. So what you want to make sure is, let's just get rid of this. So we'll go back to that dam example I showed. Here's your water surface. Right? You want to make sure that here's the depth of water. You've got, that's the depth. You've got hydrostatic forces across this entire face. That hydrostatic force, assuming this is a vertical wall, the hydrostatic force can be resolved to a single point force at mid-depth. Now you know where the centroid of this dam is. Well, if you take a dam and your centroid is up there or down there, or God forbid your centroid is over there, your dam's going to tip over. And so knowing where the centroid is going to help you design that dam. Or you're going to design the dam so that the centroid is not below the point of application of that hydrostatic force. Yeah. And there's a lot of other applications to knowing the centroid of anything. It's the point where something is going to balance, and that's a really important thing to know for a lot of cases. Other questions? So you can do this exact problem, and instead of integrating with respect to x, you can draw these rectangles with respect to y. And even though your function is you've got a function that's defined as x, you can rearrange that function, solve it for x in terms of y, and then go through the very same process, except you're going to integrate with respect to y. So let me at least show that. I have to just erase all of this.
You have to have a different function.
Well, you would take your function and rearrange it so that it would say x is equal to a function of y. So let's just get rid of that altogether. So let's try this one. Let's say we have, let's just do it this way. Say it's just a triangle. So this will be a little bit easier because we already know what the area is. So it's got a base. It's got a height. And this line is y is equal to minus h over b times x plus h. And if you want to do your rectangles this direction, you've got to rearrange this in terms of x. No, this defines the value of y for any given value of x. So if we take this equation and solve for x, we get minus b over h times y plus b. And then we can integrate that equation with respect to y. And in this case, the y component of the centroid is equal to whatever y we have, and the x component of the centroid is equal to 1/2 of x, because now we're looking at, this is your length, and the centroid's going to be halfway. And so we go back to the previous equation. It's still the same equation in that y bar is equal to the sum of yi ai over the sum of ai. And that's equal to the integral of y dA over the integral of dA. But now, let's see, dA is equal to the incremental is equal to y dy. Let's call it y of x dy. So this becomes the integral of y times y of x, which is minus b over h times y plus b dy. And the integral of the derivative of the area is the area in the area of a triangle, 1/2 the base times the height. So you multiply this through, take the integral in parts, you end up b and h are constants, so you have minus b over h y squared plus by times dy. And when you take that integral, integral of minus b over h y squared is minus b over h y cubed over 3 plus by squared over 2. And all of that is divided by 1/2 BH. And that is going to get evaluated. Now we're dealing with dy from 0 to h. And if you go through that algebra, you'll find that this is equal to h over 3. And yes?
Why isn't the dA function the same in both the numerator and the denominator?
Because in the numerator, we're taking the integral of the derivative of a. I'm sorry, in the denominator. In the numerator, we're taking the integral of y with respect to a. And dA is defined as y dx. We could put y of x dy in the denominator, and we're going to come up with that. You would come up with that. But it's a bit of a shortcut, I guess. The integral of the derivative of a function is the function. So you don't have to go through that extra step. All right. So that's the y component of the centroid. The x component of the centroid, it's still going to be x times dA over dA. But in this case, let's call it xi. And we're just going to get rid of all of this. In this case, for x, we're going to say it's x sub I becomes x over 2. dA over the integral of dA that's the integral of x over 2 dA. dA is y of x dy, x over 2 times y of x minus h over b x plus h wait a minute, y of, sorry, y of x. Yes, so it's, because we're going in the horizontal, this is going to be minus b over h. Wait a minute. Let's see. Let me back up here. X is minus b over hy plus b over 2. That's x over 2. Times x over 2 dA times y of x. Is that right? Y squared. All right. dA is equal to y of x, which is minus b over hy plus b dy. And this is divided by the area, which is 1/2 BH again, the integral of the derivative of the area. Right? Yeah, that's it. And we'll evaluate this again from 0 to h. And see. What's that?
How is X over two be?
Because this is the definition of X. Yeah.
Sorry, I was trying to look for the board and I couldn't find it. Okay.
Okay, all right. So when we evaluate this, yeah, I'm gotten a little lost here. This is still, we still have to integrate this. So that integral becomes this, let's see, 1 over 2bh times b squared over h cubed y cubed over 3 minus 2b squared over h y squared over 2 plus b squared y. And that gets evaluated from 0 to h. So I skipped a couple steps in here. You've got to multiply these fractions together, or these component parentheticals together, and then integrate it. And this is what you'll end up with. B squared over h cubed times y cubed over 3 minus 2 times b squared over h times y squared over 2 plus b squared times y. And evaluate that from 0 to h, and lo and behold, the x component of the centroid is b over 3. So if you've taken geometry or you remember your geometry, geometry would tell you that the centroid of a triangle is located at 1/3 the base and 1/3 the height. And the calculus proves that. So again, this was just another example of determining the centroid using horizontal rectangles as opposed to vertical rectangles. I'm going to stop here because it's 20 after. I believe Dr. Helferty is going to be coming in next week. I will let him know where I stopped. If you've got questions on this stuff, you're certainly free to come ask me, or you can ask him next week. He, I believe, will cover some integrals that are used in dynamics and then talk about electrical engineering as well. Are there questions? Issues, concerns, comments? Yes?
Yeah, what did you, I'm sorry, I got kind of lost where the integral of that, you mean of the numerator right there, where did you get that? Like, should it be just an x, or is there multiple x's?
This one you're talking about?
Yeah, that one on the right side, like, where did you get it?
So the integral of the derivative of the area is the area.
Okay, that makes sense.
And the area of a triangle is 1/2 the base times the height.
Okay, but where did the numerator
Up here. So again, x over 2, x is equal to minus b over h y plus b. So that's what this is, minus b over h y plus b, and that's a 1/2. And then the dA is y of x dy minus b over h y plus b dy. So it's essentially the integral of this function squared. You square that function, take that integral. All right. Anything else? All right. Enjoy the rest of the semester. Again, let me know if there's any issues or questions on this material. I will try to answer them.